Okay, this is example 3 on pipe networks. For the pipe network shown, determine the discharge in each of the pipes in liters per second if Hazen-Williams coefficient is 120 for all pipes. Stop the iterations when all the corrections are less than absolute value of 6 liters per second, which is 1% of the inflow. All pipe diameters are in millimeters and lengths in meters, so it's the given figure. So we have inflow 600 liters per second, we have outflow 300, 300, so it balances. So let's tabulate. So we have pipe AB, BE, DE, AD, and so on and so forth. Then the length in meters, you just check there. Then the diameter in meters, also check. 0.6, BE 0.5, DE 0.5, AD 0.6, and so on and so forth. Then the value of K, which is 10.67, length over diameter to the 4.87 times C sub 1 to the 1.852. So 10.67 in your calculator times 600 divided by quantity 0.6 to the 4.87 times 120 to the 1.852. So the value is 10.87. Then in the second for BA, replace 600 by 500, the diameter by 0.5. Everything is the same. So 22. Next, replace L by 600, 26.41. Then length 500, diameter 0.6 into this formula in your calculator, 9.055. Then diameter only 0.4, change 65.23. Then length 600, diameter no need to change 78.28. Then change length to 500, diameter to 0.5, 22. Change length to 400 only 17.6. Change length to 1000. 44.01, change the length to 400 for GH. This is CH, which is 1500 plus 500. So it is 52.19. Next is, let's assume the flows, QA. So let's just split 600 to 0.3. This is also 0.3. Then let's split 0.3 to 0.15, 0.15. Also here 0.3, let's make it 0.2, then this is 0.1. So 0.15 plus 0.2, 0.35, this is only 0.3, so that means this is 0.05. So this is 0.1, 0.3 minus 0.2 is 0.1. So this is also 0.1. Then you'll be the ones to supposedly assign these assumed flows. In this case, I'm the one because I present the solution to this problem. So 0.3 minus 0.15, so this is 0.15. This is also 0.15 because they are in series. 0.1 plus 0.05 is 0.15. So that's why 0.15 plus 0.15 is 0.3 or 300 liters per second. So everything is balanced. So substitute here, put it in the table. So 0.3 BE, 0.15 DE, 0.2 AD, 0.3 EG, 0.05 FG, 0.1 DF, 0.1 BC, 0.15 CH, 0.15 GH, 0.15. So it's okay. Next is KQA to the 0.852. It's no longer QA to the 1, but KQA to the 0.852. This is Hazen-Williams, remember? So 10.87 times 0.3 to the 0.852, so 3.897. 22 times 0.15 to the 0.852, 4.370. To 4 significant figures to be consistent. 26.41 times 0.2 to the 0.852, 6.703, 9.055 times 0.3 to the 0.852, 3.246, 65.23 times 0.05 to the 0.852, 5.081, 78.28 times 0.1 to the 0.852, 11.01, 22 times 0.1 to the 0.852, 3.093, 17.6 times 0.15 to the 0.852, 3.496, 44.01 times 0.15 to the 0.852, 8.741, 52.19 times 0.15 raised to 0.852, 10.37. Next is KQA to the 1.852. That is 10.87 times 0.3 raised to 1.852. And that is 1.169. 22 times 0.15 to the 1.852, 0.6555. 26.41 times 0.2 to the 1.852, 1.341. 9.055 times 0.3 to the 1.852, 0.9739. 65.23 times 0.05 to the 1.852, 0.2541. 78.28 times 0.1 to the 1.852, 1.01. 101. 22 times 0.1 to the 1.852 is 0.3093. 17.6 times 0.15 to the 1.852 is 0.5244. 44.01 times 0.15 to the 1.852 is 1.311. 52.19 times 0.15 raised to 1.852 is 1.555. Then, let's compute for the corrections before this corrected discharge. So delta Q1 is negative of the quantity 1.169 plus 0.6555 minus for DE minus 1.341, then minus for AD 0.9739 divided by 1.852. It's no longer 2 but 1.852. Quantity 3.897 plus 4.37 plus 6.703 plus 3.246. These are the pipes involved in loop 1. So the value of delta Q1 is 0.01454 or 14.54 liters per second. So it exceeds 6 liters per second. So we have to compute, we have delta Q1 prime next. Then delta Q2 in this loop involves our DE. So DE 1.341, negative of quantity 1.341, EG 0.2541 plus, then minus FG. FG is 1.101. FG, then minus DF. DF is 0.3093 divided by 1.852 quantity for DE 6.703, for EG 5.081, that's it. For FG 11.01, that's it. For DF 3.093. So delta Q2 is negative 0.003855, or this is negative 3.855 liters per second, which is below the absolute value of 6. So this is supposedly acceptable, but delta Q1 is not acceptable. So everything must be recalculated or must be iterated again to reduce the error or the delta Q. Then we also have delta Q3. Involves our BC, CH, GH, EG, and BE. There are 5 pipes. So delta Q3 is negative of quantity BC 0.5244, CH plus 1.311 minus GH minus 1.555, then minus EG 0.2541 minus 0.2541, then minus BE minus 0.6555 divided by 1.852 times quantity BC 3.496, CH 8.741, GH 10.37, plus EG 5.081 EG, plus BE 4.370. So that's it. Computing, delta Q3 is 0.0106 cubic meter per second. This is 10.6 liters per second. It is outside of 6 liters per second. So that's why we have to recompute and modify the new assumed value. So for QA1, it is equal to 0.3, this member AB here, plus delta Q1. So 0.3 plus 0.01454 to 4 significant figures, 0.3145. Then BE is common to loops 1 and 3. So BE is 0.15 plus delta Q1 plus 0.01454. Then minus delta Q3 minus 0.0106. So the result 0.1539. DE is common to loops 1 and 2. So for loop 1, 0.2 minus delta Q1 minus 0.01454, then plus delta Q2 plus negative 0.003855. The answer is 0.1816. Again, for DE, QA1 of DE is 0.2 previous, minus delta Q1 minus 0.01454, then plus delta Q2 plus negative 0.003855. So you get 0.1816 to 4 significant figures. AD. This is AD, so it is only previous 0.3, then minus delta Q1. It is opposite, so minus 0.01454. It is 0.2855. EG. EG is common to loops 2 and 3. So EG is previous 0.05, 0.05 plus delta Q2 plus negative 0.003855. Then minus delta Q3 minus 0.01060, and you'll get 0.03554. FG. This is FG. It is only previous 0.1, then minus delta Q2. 0.1 minus negative of 0.003855, so it increases 0.1039 cubic meter per second. DF, it's the same. 0.1 minus negative 0.003855, so it's 0.1039. This should be equal. Then BC is 0.15 plus delta Q3 only. 0.15 plus 0.0106, 0.1606. CH is the same. 0.15 plus delta Q3, so 0.1606. GH is 0.15 minus delta Q3. 0.15 minus delta Q3. 0.15 minus 0.0106, 0.1394. So that's it. So next, let's compute KQA1 to the 0.852. That is 10.87 times 0.3145 raised to 0.852. That is 4.057. 22 times 0.1539 to the 0.852, 4.466. 26.41 times 0.1816 to the 0.852, 6.174. 9.055 times 0.2855 raised to 0.852, 3.112. 65.23 times 0.03554 to the 0.852, 3.799. 78.28 times 0.1039 to the 0.852, 11.37. 22 times 0.1039 to the 0.852, 3.196. 17.6 times 0.1606 to the 0.852. 3.705, 44.01 times 0.1606 to the 0.852. 9.265, 52.19 times 0.13, 94 raised to 0.852. 9.739. Then here we have to evaluate K, Q, A sub 1 raised to 1.852. That is 10.87 times 0.3145 to the 1.852. 1.276. 22 times 0.1539 to the 1.852. 0.6874. 26.41 times 0.1816 to the 1.852. 1.121. 9.055 times 0.2855 raised to 1.852. 0.8885. 65.23 times 0.03554 to the 1.852. 0.135. 78.28 times 0.1039 to the 1.852. 1.181. 22 times 0.1039 to the 1.852. 0.332. 17.6 times 0.1606 to the 1.852. 0.595. 44.01 times 0.1606 to the 1.852. 1.488. 52.19 times 0.1394 raised to 1.852. 1.358. Next, let's compute delta Q1 prime. First, so negative of 1.276 plus 0.6874 minus 1.121 minus 0.885. So plus, plus, minus, minus. Divided by 1.852 times quantity 4.057, 4.466, 6.174, 3.112. The formula was negative summation of KQA to the 1.852, summation in the numerator, then divide by 1.52, then summation of KQA to the 0.852 in the denominator. So delta Q1 prime is 0.001398. This is 1.398 liter per second, which is below 6. So this is acceptable, hoping that the other corrections are also acceptable. Delta Q2 prime is equal to negative of quantity DE 1.121 positive plus EG 0.135 positive minus FG 1.181 minus DF 0.332 divided by 1.852 quantity DE 6.174 EG 3.799 then FG 11.37 DF 3.196. So delta Q2 prime is positive 0.005754 cubic meter per second. This is 5.754 less than 6, so acceptable also, hoping that delta Q3 prime is also acceptable so that we can now finalize our discharges. Delta Q3 prime is equal to negative of quantity BC 0.595 CH plus CH 1.488 minus GH 1.358, this one, then minus EG 0.135 minus BE 0.6874 divided by quantity 1.52 times quantity KQA 1 to the 0.852 for BC 3.705, then CH plus 9.265 plus GH 9.739 plus EG 3.799 plus BE 4.466. So this is equal to 0.001698, which is 1.698 liter per second. So all corrections are below 6 liters per second. So that means we can now finalize the discharge. So for AB, it is 0.3145 plus delta Q1 prime. 0.314 quantity 0.3145 plus 0.001398 close times 1000 to convert it to liters per second. So 315.9 liters per second. For BE, common to loops 1 and 3. So for BE, 0.1539 plus delta Q1 prime plus 0.001398, then minus delta Q3 prime minus 0.001698, and the answer times 1000, 153.6. For DE, 0.1816, DE is common to 1 and 2. So 0.1816 minus delta Q1 prime minus 0.001398 plus delta Q2 prime plus 0.005754, then times 1000, you'll get 186.0 liters per second. For AD, this one, it is only 0.2855, then minus delta Q1 prime minus 0.001398 times 1000 to 84.1. Then for EG, common to 2 and 3. So EG, 0.03554, quantity 0.03554 plus delta Q2 prime plus 0.005754, then minus delta Q3 prime, 0.001698 times 1000, you'll get 39.6 for EG. Then FG, 0.1039 minus delta Q2 prime minus 0.005754 times 1000, 98.15. So expect also for DF to be the same. 0.1039 minus delta Q2 prime 0.005754 times 1000, 98.15. Then for BC, it is only 0.1606 plus delta Q3 prime plus 0.001698. So 0.1606 plus 0.001698 times 1000, 162.3 liters per second. CH, it should be the same as BC. So 0.1606 plus delta Q3 prime 0.001698 times 1000, 162.3. Then finally GH, 0.1394 minus delta Q3 prime minus 0.001698. So you get times 1000, you get 137.7. So to check, AB 359.9 plus AD 284.1 is 600 liters per second. In this junction, BE 153.6 plus DE 186 minus 300, then minus EG minus 39.6, it should be 0. Then at this junction here, CH 162.3 plus GH 137.7 is 300 liters per second. So that's checked. So that's why these are the final answers. I hope you are able to follow the solution. If you find it faster, you can stop the video, then calculate all these values, then compute these values. How are they calculated? So this is the last example, and all the pi formulas are well represented to examples 1, 2, and 3.